All right, here we go. Picking up where we left off. We had a lot of these properties yesterday. We were kind of using them, and I kind of summarized them as we went. But here's kind of like a non-exhaustive list, okay, with some examples. So if we are multiplying and the bases are the same, what do we do with the exponents? We add them, right? So remember, it comes down one rung on the operational ladder. A multiplication problem turns into an addition problem, okay? And then the second side of that same coin is division. A division problem turns into a subtraction problem. So if you're dividing and the bases are same, then you subtract the exponents. Now, it is important to note there that when you subtract the exponents, the answer always goes in the numerator, okay? The answer always goes in the numerator, just like over 1. We saw with 3 yesterday, anything to the 0 power is 1, except 0, okay? You can't be 0 because 0 to the 0 is equal to something else. You'll learn that in calculus. But any other number to the 0 power is 1. And it comes from the rule of exponents, okay? This right here, when you raise a power to a power, what do you do with the exponents? What do you do with M and N? You multiply them. Yeah. Again, this is one rung lower. This is exponentiation right here, and it turns into multiplication. All right? Now, this one here is kind of new, but you've seen it before. If you have multiple factors, like U and V, factors are what applied together? Factors are what applied together? Multiplied. Yeah, there you go. I was trying to give you a hand. Yeah, they're multiplied together. Or divided. They could also be divided. The rules of exponents, as we pointed out yesterday when we were saying Worcestershire, the rules of exponents only work with factors. Factors implies, thank you, what operation? Multiplication. Good. So the rules of exponents only work with multiplication / factors, okay? So if you have multiple factors and the whole quantity is raised to a power, you can actually use rule number 4 on each factor. That is, you can distribute the exponent and get u to the m times v to the m, okay? But it only works with factors, not terms. All right, so let's look at this example. If you have 3x squared times y, all raised to the 3rd power, because that's 3 times x squared times y, those are factors. What I would do, in the beginning especially, is to help myself by putting little 1s there so that I have targets for my distributive property. So that's going to be 3 times 1, 3 times 2, 3 times 1. All right, and you get 3 cubed, x to the 6th, y to the 3rd. And, of course, 3 cubed is 27. All right? Most people who don't or refuse for whatever reason to put little 1s there as exponents, most of them come up with x to the 6th. Most of them come up with y cubed. But guess what the most common error is? Instead of calling it 3 cubed, guess what a lot of people call that? 9. They know they have to multiply something, but they go ahead and multiply 3 times 3 and get 9, instead of multiplying the implicit exponent of 1 to get 3 cubed, which is actually 27. So that would be a careless mistake. So a way to avoid those careless mistakes, and there's no shame in doing this again, is just to add little targets, little exponents, okay? Do that. There's no shame in that. All right. Now let's look at this same rule. What if it were like u plus v to the mth power? Do you think that that would equal, I'll put a little question mark there, u to the mth plus v to the mth? Yes. The rules of exponents work with factors. Factors imply multiplication or division. What are we doing with u and v there? We are adding them. That means u and v are not factors. They are terms. Right. So this is a big no. This is a big no. Those are not the same. But that is the one thing that students desperately try to do. And regardless of your level of desperation, it doesn't increase the likelihood of that ever being correct, okay? It never works. So someone last week said, so what would you do there? And I was like, that's a very challenging thing. So let's just say I had like x plus 2 squared, right? It's kind of like an early sin for students to call that x squared plus 4, right? That would be just distributing the 2. That's not right, because you know you have to FOIL that out. And you know that there's a middle term called 4x. What if that were x plus 2 cubed? Oh, now you're going to have to write them side by side and just expand it out. So that's a much harder thing. That's binomial expansion, and that's a much more arduous task. It's not as simple as just distributing it to the terms. So the rules of exponents only work with, what's the F word? Factors. Yeah, factors. Which implies which two operations? Multiplication or division. Okay, very good. All right, the second side of that same coin, if you're dividing two factors to a certain power, you can distribute that to the top and bottom. I'll get it and give you a break. There we go. There you go. Okay. So something like this. 2/3 quantity to the fourth, that's the same as 2 to the fourth, 3 to the fourth, okay? All right, so let's learn a new exponent. We've been working with integer exponents, positive integer exponents. Now we're going to work with negative integer exponents, okay? So if you have something with a negative exponent, b to the negative n, does anyone know how to handle negative exponents? Or what it means? It's a fraction. What'd you say? Over here? Yeah, put a division bar. Fraction, division, kind of related. Yeah. That's the same thing as 1 over b to the positive n, okay? So a negative exponent is really a fraction in disguise. A fraction in disguise is a negative exponent. Now here's one way to think about it. If that's b to the negative n, you can think about it as being over 1. As long as it's a factor and not a term, if you want to get rid of a negative exponent, all you have to do is take that factor to the other side of the fraction. If it's in the top, take it to the bottom. If it's in the bottom, take it to the top, and change the sign of the exponent, okay? So b to the negative n over 1 is the same as 1 over b to the positive n. All right? Very, very important. So like if you have 2 to the negative third, is that equal to negative 6? Is it equal to negative 8? No. Put it over 1. Take it to the bottom. It's equal to 1 over 2 to the positive third. And what is now 2 cubed? 8. It is 1/8. 2 to the negative third is 1 over 2 cubed. All right? You don't have to have negative exponents always in the top. You could have like 3 over 2 to the negative second. If you wanted to simplify that, what would you do? You could bring that factor to the top and call it 3 times 2 to the what? Positive second. You just changed the sign. And now that's 3 times 4, which is 12. Okay? If you have a negative exponent on a factor, take it to the other side. What if you had like a 5 and you wanted to write it with a negative exponent? Well, let's see. Put it over 1, bring it to the bottom. That means it's 1 over 5 to the what power? Negative first. Yeah. So it doesn't matter if the exponent is positive or negative. As long as it's a factor, if you bring it to the other side, high to low, low to high, you change the sign. Whatever it was, it's now the opposite, okay? Now, here's an error alert. It only works with factors. So if you have like 1 over 2 to the negative second plus 3 to the negative second, these two down here are terms because there's a plus sign, right? You cannot bring that to the top, and say it's 2 to the positive second plus 3 to the positive second. That does not work, okay? It's, again, because those two in the bottom are terms, not factors. The rules of exponents work with factors, things that are multiplied or divided, not added or subtracted, okay? All right, so let's try it out. Example 2, simplify the following exponential expressions if possible. Ooh, if possible. All right, so letter A, 2 over x to the negative fourth. We have one term. There's no plus or minus sign, so that expression is a single term. And there's two factors, one on the top and bottom. We want to get rid of the negative exponents. We're going to use that as kind of our target. So bring that to the top, and you get 2 times x to the what? Positive fourth. Done. Piece of cake. Easy, yeah. First one's always easy. All right, questions on that one?
Why wouldn't you put the 2 on the bottom?
You can, if you want. But what's the exponent on the 2 right now when it's in the numerator? What's implied? That it's a 1, okay? So if you want to bring the 2 in the bottom, you could leave the x to the fourth on top. Now that's going to be 2 to the what? Negative first, right. And you could do that, right? It just doesn't look as pretty. So the 2 already has a positive exponent, so we kind of leave it where it's at. But, again, you can take it to the other side. All right. Try this one on your own. Get rid of the negative exponent. All right, so if you want, put it over 1, right? Help yourself, help yourself. What is actually being raised to the negative second power, the x or the 3x? Just the x. You got to be very careful about what you associate exponents with. Unless there's grouping symbols like parentheses, it's only associated with that first element down to the bottom left. So you're only bringing the x to the bottom, the 3 stays put, and it's 3 over x squared. All right? So again, if you wanted to bring the 3 to the bottom with it, you could, but it would be 3 to the negative first in the bottom. So 3 over x squared is the answer. Correct. Yeah, and so if you want, like I said, it doesn't matter if it's negative or positive. Right now our goal is to get rid of the negatives, but if you wanted to get rid of positive exponents, you could have brought the 3 to the bottom. You could call that x to the negative second over 3 to the negative first. That works. It's the same thing. Okay? So regardless of where it lives, regardless of what the exponent sign is, as long as it's multiplied or divided, bring it to the other side, change the side, or sign, sorry. Okay? All right. How about this guy here? What's being raised to the negative second power? The quantity 3x. So if you put that over 1, you bring the entire quantity down. And now what happens to the sign of the exponent? It changes signs. So now it's positive. And then from there, we can use rule number 5. Those are both to the first power. So we can distribute that 2, and it becomes 1 over 3 squared. What's 3 squared? 9x squared. So 1 over 9x squared would be the answer. So really assess the problem before you jump in. What do the exponents associate themselves with? Are there grouping symbols that make it a quantity, or is it just that first little element, that first factor? To the bottom left. All right, letter D. Take a minute. Come up with a plan for that. Take a minute. Do it. Simplify it. Uh-huh. The 2 to the, yeah. So you didn't show that intermediate step. The intermediate step would be this.
Okay, and then
right, and now because that's 3 to the first, x to the first.
Oh.
Yeah, it'd be 3 squared, x squared. Mm-hmm. All right, on this one, how many terms do you see? Terms are separated by pluses or minuses. I don't see any plus or minus signs. So that right there is one term. If I had like plus 2, now there'd be a second term, right? So there's only one term, but it has 4 factors or factor groups. The 4, the y cubed, the 2, and then this little dude here. All right, so there's 4 factor groups. So our goal is to combine like factors. So the first thing I'm going to notice is the 4 and the 2, those divide out, right? So I'm going to put the shelf there. It's easier to stack stuff on shelves if you already have the shelves, right? Right? You ever try to put something on a shelf that's not there? What happens? Falls, right? So 4 divided by 2 is 2, all right? So that takes care of the numbers. Now I'm going to focus on the y's. So in the top, y cubed looks like he's good, but I've got these grouping symbols here, all right? And our goal is to kind of tear down the wall. So what do we do with the 2 and the 4? Multiply or add? Multiply. So we get y to the 8th, all right? Now from here, there's several different ways you can go, right? There's usually more than one route to San Antonio. So same thing here. If you use the rule of exponents, that's 2 times y. Remember, when you are dividing and the bases are the same, you subtract the exponent. So that would be 3 minus 8. And remember, that goes in the numerator. So I'm showing a couple of extra steps there. Now, in terms of notation, notice I'm kind of out of room on the bottom, so you can either kind of keep going underneath the verse of ice, or you can kind of create a new column here, and that becomes 2y to the negative 5th. All right, so now if our goal is to get rid of the negative exponents, I can put that over 1, and what goes to the bottom? Y to the 5th, just the y to the 5th, right? So the 2 stays up top, and you get 2 over y to the 5th. So that would be the preferred answer, 2 over y to the 5th. All right, now the other way to do that that's a little bit faster, if you know you don't want negative exponents, is if you look at these y's right there, you have more y factors where? Top or bottom? In the bottom. And you could just realize that there's 3 in common. So 3 of them will divide out, leaving 5 in the bottom. And you can go straight from here to here. All right, so if you don't want to use those rules where you subtract, that's fine, as long as you end up with the right answer. Okay, but you can see that those rules do work. All right, so that takes care of negative exponents, right? A negative exponent is what in this, guys? A fraction. A fraction. Take it to the other side, change the sign. Okay, so now speaking of fractions, we are going to look at fractional exponents, not fractions themselves, but fractions in exponents. Another name for a fraction is a rational number. Okay, a rational number. The key word in rational is ratio, not al. Number. Okay, number. So here we go. If you see a fractional exponent, and I did write it kind of as a slant, because when you're writing fractions in the exponents, it gets kind of small. But when you use the slanted division bar, just make sure that your numerator and denominator are single elements. Otherwise, you need parentheses. So b raised to the m divided by nth power ends up being the nth root of b to the nth power. That's one way. Or you could say it's the nth root of b quantity raised to the nth power. This one's just a little bit more efficient. Okay, it's just a matter of order of operation. Okay, so look at that right there. This is the denominator in the exponent, yes? And it ends up going right here in the problem. We call this number right here the root or the root index, but you could think of it as the root. That's fine. Okay, so like the square root, cube root, fourth root. So to help you remember that the root goes in the denominator, again, you can kind of think of like a fraction bar, right? Let the fraction be the ground. And you got like the number 1 up here, which blossoms into a beautiful flower. And what grows underground? The roots. Okay? So roots grow underground, they're in the denominator. So the roots become the denominator. All right? And this m, this is really like m over 1. So it stays in the same location. All right? So we can then say that a fractional exponent is not a fraction in disguise, but a radical. There's a lag here. There it is. A fractional exponent is a what in disguise? A radical in disguise. And vice versa. A radical in disguise is a fractional exponent. Okay? So let's kind of, we looked at this yesterday. If you have like the square root of x, that's the same as x to the what power? 1/2. Not second power, but to the 1/2 power. Remember, if there's no index drawn in there, it's implied to be a 2. But after that, we have to show it. So the cube root of x is x to the 1/3. Similarly, the fourth root of x is x to the 1/4, so on and so forth. Okay? Now, you can imagine that if you had something under the radical other than a 1, like if that were x cubed, that would no longer be just x to the 1/2, but x to the 3/2, right? The 3 would kind of stay in the numerator. If that were the cube root of x squared, it would now be not x to the 1/3, but x to the 2/3, so on and so forth. The fourth root of x to the 5th would be x to the 5/4. Yeah. Okay. What's important to remember is that the root or the root index goes in the denominator of the exponent. Fractional exponents are radicals in disguise. All right. Let's try it out. Simplify the following if possible. 3 times the fourth root of x squared. 3 times the fourth root of x squared. Fourth root of x squared. We got to simplify that. Is it 7? I'm guessing. Is it 7? I don't think so. What can we do to simplify that? It looks pretty good to me. Hey, there you go. If you ever see a radical in an expression, it's going to be a lot easier to simplify it if you write that radical as a fractional exponent. Why? We know how to work with fractions, right? It's not as easy to think in terms of radicals. So let's go ahead and rewrite that. That's 3 times x to the what power? It'll become that, but what is it right now? 2 fourths. And now you're like, oh, 2/4. What's up, 1/2, right? Good. See, It's easy. You see 2/4, you say 1/2. And now, let's practice. That could be a final answer right there. But let's go ahead and practice then putting it back into radical form. So 3x to the 1/2 now becomes 3 times square root of x. There you go. So it turns out that the 4th root of x squared is the exact same thing as the square root of x. We didn't really know that maybe at first, but once we put it as a fractional exponent, it was obvious, all right? So there you go. There's a new strategy. If you see radicals, write them as fractional exponents. Letter B. All right. Okay. What should we do first? Yeah, fractional exponent. It works so well over here. Maybe it'll work again. Who knows? So let's write that as 4 over 5 times 2 to the what power? 5 seconds. 5 halves. Yeah, 5 halves. The 5 is already there. It's the square root, so the 2 from the square root goes in the denominator. Cool. Now what? Does anything combine from there? Not real obviously, but we saw a little trick yesterday. I've got bases of 5, 2, and 4. Can I write any of those in terms of each other? 4 and 2. We saw that yesterday. So let's go ahead and call 4 2 squared. All over 5 times 2 to the 5 halves. And now you get excited. Ooh, 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 ooh. I got common bases. And I'm dividing them. So if you want to use the rule here, the 5 is in the bottom. Using the rule in the numerator, it's 2 to the, we subtract, right? So it's going to be 2 minus 5 halves. 2 to the, using the rule, something's divided, so we subtract. 2 minus 5 halves. Now, eventually, maybe you won't have to show the 2 minus 5 halves. Why do you think we worked so hard with fractions the last 2 days? Because we're going to be doing a lot of this stuff, all right? So what is 2 minus 5 halves? Well, 2 is how many halves? 4, right? You have 2 pies, you cut each in half, now you got 4 halves, right? Simply multiplying the 2 by 2 over 2 means now you have 4 halves minus 5 halves. And that's easy to do in your head, right? What is 4 minus 5? Negative 1. Yeah, so 4 halves minus 5 halves is negative 1 half. All of those fractions that we just quizzed over, they are going to show up a lot in simplifying these expressions. And so that's why I want to be able to do them efficiently. If you still need to go off to the side and get a common denominator, that's fine. It's going to take you a little longer. Do it off to the side. You need to get it right before you can get efficient, all right? Now let's go ahead and practice getting rid of both the negative and the fractional exponent for our final answer. Which one do you think we should get rid of first, the negative or the fraction? The negative, yeah, it's obvious. When you walk up to the number, the first thing you see is negative, right? So get rid of that first. So using the previous rule, we'll slide that factor to the bottom, leaving a 1. It's like dividing out with itself, so it leaves a 1. The 5 is down there, times 2 to the what power? Positive 1 half, good. And now I'm going to squeeze it down in here. Now we'll put that back under a radical. That's the what of 2? Square root of 2, yeah. So 1 over 5 square root of 2 is a fine answer. Later on, we'll be rationalizing the denominator if there's a radical by multiplying by square root of 2 over square root of 2. But right now, we'll leave that. So you can call that square root of 2 over 10 if you want. That would look like this. Let me just show you that. Radicals in the denominator in general are fine, but in the second semester when we get to the unit circle, we're going to want to get rid of them. So if you multiply by a clever form of 1, and you multiply straight across, you get the square root of 2. And then, of course, the square root of 2 times the square root of 2 is just 2, or the square root of 4. And then 5 times 2 is 10. So that's another version of it. Square root of 2 over 10, or 1 over 5 square root of 2. I think they're both pretty cute. So I wouldn't like pick favorites, like which one is more simplified. So anyway. Okay, here's a confidence boost for y'all. Letter C. You do. What should step 1 be? Change them into fractional exponents. Excellent. So that's going to be x to the 1/2 times x to the 1/3. And now the bases are the same, so you add the exponent. So here's where that fraction work comes in again. 1/2 plus 1/3. With a little practice eventually, you don't need to do that off to the side. You could just do it in your head with the crisscross method, right? What is it? Off to the side, 1/2 plus 1/3, they're co-primes, so 1 times 3 plus 2 times 1, all over 2 times 3, 5, 6, right? Yeah. So again, we're going to see a lot of fractions. If you need to do this every time, try to practice doing some of that in your head, but I'd rather you get it right than make a careless mistake, okay? X to the 5/6 is a decent answer, but let's practice now putting it back into radical format. That's going to be the what root? The 6th root of x to the 5th. That's the final answer. What would make a fantastic other choice on a test question for a multiple choice question? Yeah, flipping those around and calling it the 5th root of x to the 6th. Yeah. That would be the morsel on the hook that you wouldn't want to take, right? That's the bait answer, right? Yeah. I had Art 1 many years ago downstairs with the great teacher. Yeah. Miss Smithers. All right. If you're listening, Miss Smithers. Okay. Any questions on part C? She might watch these videos. You never know. Okay, so let's go ahead then and go to D. Whoa. Let's do this one together, because we got some strategies to talk about. How many terms do we see? One. That is one term, okay? But it has like 3 factor groups. The numerator is a blob squared. That's one factor group. The bottom has a 3, and then a square root of x to the 5th. What has our step 1 been every time we've had radicals? Yep, and we're going to do that first, again, okay? So don't worry about that blob squared. Just write it as blob squared. Now it's going to be 2 times x to the what power in the numerator? I will in the next step. If I do too many things in one step, I might trip, right? 2/5, yeah. So that's 2 times x to the 2/5 all squared. There's my new numerator. And in the denominator, I get 3 times x to the 5/2, yeah. Okay, so now I reassess, and I'm like, okay, I've got fractions there. Those are multiplied, so I can distribute the exponents. I'm going to put a little 1 on the 2 so that I give myself a target for my distributive process. So that's 2 squared, which you can go ahead and call 4. And that's x to the 2/5 times 2 is what? 4/5, right? Because that's really 2 over 1. You just multiply straight across. X to the 4/5. Make that x a little bigger. There we go. And then all of that's over 3x to the 5/2. Okay, cool. Now I need to go to another column here. And I build the shelf. 4 and 3 are co-prime, so they don't divide out. But my x's are common factors. So using the rule, I do what with those 2 exponents? Subtract. Good. So I'll go ahead and write it here as an intermediate step. It's going to be 4/5 minus 5/2. And here's where that little crisscross applesauce thing comes in handy. You don't have to do it off to the side. That's going to be an 8 minus 25. What's 8 minus 25? Negative 17 all over 5 times 2, which is 10. We're going to be working with a lot of interesting fractions like that. X to the negative 17 tenths. So that is simplified. We have one representative factor of each type. So let's go ahead and practice now getting rid of both the negative and the fraction. So like we did before, we'll get rid of the negative first. We'll bring that to the bottom. So now 3 gets a new friend, x to the 17/10 positive. And then I need one more column for the final answer. That's 4 over 3, and it's the what root? 10th root, yeah, of x to the 17th power. Beautiful, beautiful, beautiful. Comments, questions? Pretty cool, huh? Kind of fun. Emphasis on fun, not kinda. The last step? Well, because I have x factored to a negative exponent, I can slide that factor to the bottom and change the sign of the exponent. Oh, how did I get these numbers, or how did I get negative 17/10 from those numbers? Oh, I added them. Okay, I did the little crisscross method. That's what we've been doing the last couple of days. 4 times 2 is 8, minus 5 times 5 is 25. All over the product, 5 times 2 is 10. Okay, so that's the thing that I'm emphasizing. If you need to do that off to the side, go for it. Do it off to the side, but it's going to happen on such a regular basis that you should try to get more comfortable. I mean, if you write that step there, that's good. I can understand that step. But then they're co-prime, 2 and 5, so try that little crisscross applesauce thing in your head, right? It's called growth, right? And growth requires a temporary release, a surrender of security. So that's okay. You're going to be a little bit uncomfortable in the beginning. And then you're going to get comfortable. I'm going to make you uncomfortable again. All right. 4 to the 3 halves. 4 to the 3 halves. 4 to the 3 halves. Now, notice there's no variables in here. Yay. That means that this is equal to a number, and I want you to simplify it. So, without me guiding you, take a minute and see if you can come up with an integer version of that, a nice number. Good. I see some correct answers. What's 3 times 1/2? 1.5, or 3 halves, right? Yeah. 3 times 1/2 is 3 halves. What's 1/2 times 3? Same thing, right? 3 halves. Multiplication is commutative. So if you write 3 halves as 3 times 1/2 or 1/2 times 3, the only difference then between the left and the right is the order of operations. The one on the left says take 4, cube it, make it bigger, and then square root it, make it smaller. Whereas the one on the right says take 4, square root it first, make it smaller, and then cube it, make it bigger. So what do we say would be easier without a calculator? Small than big or big than small? Small than big. Okay, now these numbers are still relatively small that it doesn't matter which way you do, but I would do the method on the right-hand side first. Because the square root of 4 is what? 2, and then what's 2 cubed? 8, and that's the answer. Whereas over here, you're doing 4 cubed, which is 16 times 4, 64, and then the square root of 64, 8, right? But you could see how quickly 64, if it's a different base, like a 5 or a 6, can get way out of hand pretty quickly. So look to go small before you go big. Look to take square roots, cube roots before you exponentiate. So yeah, this becomes the square root of 4, which is 2 cubed, and 2 cubed is 8. So that's 4 to the 3 halves is 8 in disguise, right? So if you play a sport and you got 8 on the back of your jersey, you can replace it with 4 to the 3 halves, and everybody will know who you are still, right? Great play, 4 to the 3 halves. What? You should try it. People will start talking about you. Okay, any questions? Having a good time so far for a Friday? Fun Friday. We have fun every day, but also on Friday. Okay. So here's the summary with the new ones added, 7, 8, and 9. So again, number 7, if you have u to the negative nth power, it's the same as 1 over n. The mth root of u to the n is u to the n divided by m. And finally, number 9. Number 9 is what you should be shooting for, okay? If you have a radical in the denominator, we're going to be really interested in getting rid of the radical and bringing it to the top. You should shoot to go straight from the left side to the right side in a single step, okay? So you would get rid of the radical first. In the denominator, that's u to the n divided by m. And then when you bring it to the top, it becomes negative, okay? And then similarly, if you start with the right side, you want to be able to write it back like the left. So you get rid of the negative first, which puts the u to the n over m in the bottom, and then you write it back as a radical. So if you need to show an intermediate step in between there, temporarily, that's fine. But keep working at it. You should be able to eventually look at the left and go right to the right and vice versa. All right, that's a good place to stop for today. We have some summaries, and then we have only 3 more problems left in this section. So remember, there's a worksheet. I will not be taking it up, but you should practice, 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 practice. And the key is posted with all the answers in the annotation. So if you get gerstucken, you can get understucken by looking at the key or to see if you're right. We'll finish pretty easily on Tuesday. We're going to roll right into the next section, and then we're going to test sometime next week. I'll let you know on Tuesday. All right. Have a splendid 3-day weekend.